wanting them to be prepared for the needs of tomorrow. When there is a world that's accelerating as quickly as it is, it's hard to even imagine what's going on tomorrow, much less how to prepare them best. But there are ways. Unfortunately, the ways that we have aren't always the ways that we need to have. So the classrooms and the tools of yesterday and often today are not always the tools that we need for the education of tomorrow. And in order to really keep pace with the needs that are rushing toward us in tomorrow's world, we need today's education to keep pace with that as well. Sometimes it doesn't feel like that's happening. When you're in the middle of the classroom, I've been a teacher myself, it can feel like the world is rushing by, and it's extremely hard to imagine sometimes how to grab control of that and to think about how you can best take advantage of those opportunities for getting kids to where they need to be. So that's why we're here today. I'm here today to say, relax, there is a way to do this. We can put you in the driver's seat, help you think about ways that can really help accelerate students' conceptual understanding, get them prepared for the needs of tomorrow, and do that in some innovative and interesting ways. I'm going to talk about 3 different sections today. I'm going to give some overview and background about us at the Concrete Consortium, the work and the research that we do, the kinds of things that we're interested in, and about the world as it is today. I'm going to give some examples of practices of science and engineering and examples of how technology can exemplify those practices and how we can use those for helping students understand things more easily, more quickly, more effectively than we could without. And then I'll give you some quick tips on how you can put those into action and get some of the resources and things that I've been showing today. So starting out with an overview and background. Before we do that, I'm going to take a quick poll just to get us acquainted with you out there. I'm interested in how often you use technology in your teaching. Do you use it? Really not that much. Maybe occasionally, once a month. Are you one of those people who every week you try to find something interesting to do, or do you find yourself almost every day using technology? We've got a poll option that Sharon should be able to put up, and you should be able to choose A, B, C, or D, and then we'll get a sense of what people are doing out there with technology. Now, I don't see the poll, but it may be coming up right now. Sharon, I'll let you facilitate. There we are. So this is great. I'm seeing a big chunk of early adopters here, people who say almost every day I'm using technology in my classroom, almost 3/4 of you out there. Another quarter almost say once per week. A few folks saying I really need to get my feet wet more with this, using it once a month, but there's nobody right now who's saying, not ever. That's wonderful because there are a bunch of resources and there's a lot of research on how technology can effectively help us, help our students in these ideas. I'm going to talk about a lot of that today. So I think you'll find some things that are very interesting for you. Hopefully you'll find some things that are enlightening and new and give you some new perspectives. So this is a quote I love. Chris Dixon said it best. It's really easy to predict the future. If you're looking at the internet, anything that hasn't transformed yet, it will. We've seen this happen, and we've seen it happen time and time again. The music industry flipped in years. The entertainment industry flipped almost faster. The news industry is changing under our feet. So what's next is very clear, and it's really in front of us right now. Education is changing at the same rate. But the question of what the future of education is still very open. We're still not exactly sure what we're going to see in the next generations coming up with education. We do know that it's changing quickly, and I can tell you, and you probably know this as well, but from firsthand experience, that when you're dealing with the internet, it puts dog years absolutely to shame. The changes that happen are amazing. Sometimes it's hard to get a handle for exactly how quickly that's happening. So what I like to do is to put it in a little bit of perspective and to think about the students that we see in front of us all the time. So one thing that's hard to do is to look ahead and predict the future. Yogi Berra said it best, and predictions are hard, especially about the future. In technology, that's especially so. One thing we can do, though, is to think about things that have just recently happened and the changes that have recently gone on. So to do that, I want to look back a little bit, but think ahead. Let's think about today's third grade students. It will take them about 9 years or so to graduate. Let's look back and think about what's happened in the last 9 years. If we think about the things that have been introduced, Twitter has been introduced, Gmail has been introduced, the iPhone has come into existence in that amount of time. We should expect that by the time third grade students graduate, the ones you're seeing in your classrooms right now probably, that's something that changes our lives as much as the iPhone has, that is just being introduced today and will be changing their lives then. If we think about this a little bit further and look back, it gets even more interesting. Think about today's kindergartners. We should expect to see something on the order of YouTube, Google Maps, Facebook. Those things that might be changing your everyday life never existed in that amount of time. The things that are happening today will be changing their lives in unpredictable ways in the future. And if we go back one more step, it gets really interesting. Just look a few years more back. Think about the preschoolers that are just about to come into the elementary school. Those are the ones who we will be teaching any day now. Something on the order of the iPod, accurate GPS signals that transform the way we move around everywhere today. Google, the existence of Google came in 1999 in just about that same amount of time. So there's something out there that we can't predict right now that will be changing preschoolers' lives that much with technology. It's absolutely stunning to think about, and it makes us realize that it's very important to prepare these students for a future that we can't predict, but we know will involve science, math, and engineering in new ways that we can't imagine. It's especially important when we think about where we are today, because the situation is not where we'd like it to be. If we look at a group of students who enter high school today, and we think about some of the ones that drop out, some of them express interest but then lose it. Of the ones who are left over who are going to college and accepted, only 23% of those announce an intended major in STEM in their freshman year. But by the time we get to senior year of college, 38% of those have dropped the major. Now, why is that important? Well, it's important because what's happening out there is exactly the other way around. There are 1.8 million STEM jobs that we expect to have unfilled by 2018. And I've talked to people in STEM industries who are shaking in their boots. They don't know what to do because they can't find people yet today, and they see the need growing. At the same time, 72% of citizens aren't prepared to read major newspaper articles about science today. So whether you're thinking about preparing the students for the STEM jobs of tomorrow or preparing them simply to be citizens going into the ballot boxes of tomorrow, it's clear that there's a long way to go in getting them to understand science, math, and engineering. And the place to start with that interest, and research shows this, is that much of that interest needs to happen, especially for STEM careers early on. That by the time students start to reach middle school, their interests are getting locked in. By the time they reach high school, they're fairly decided on what their careers will be. But that interest can be started in elementary school, and that can launch people into whole new careers that they never would have imagined otherwise. So that's one of the questions we're interested in at the Concord Consortium, and we're specifically interested in how we can help use technology to inspire and move students toward understanding and careers and interests in science, math, and engineering. A little bit about us. We are a nonprofit organization. We are located in Concord, Massachusetts, and with a branch in the Bay Area in California as well. And we've been around for 20 years designing educational technology to help students learn science, math, and engineering. All of our work is focused on opening up new vistas, doing cutting-edge work, and really making the invisible visible and explorable in ways that bring out the inner scientist in everyone. And I hope to show you some examples of our work today on research on learning and on how technology can help that. And then I'll show you some examples of work that we're doing together with McGraw-Hill, because we've been very excited to partner with McGraw-Hill on developing interactive technologies for inclusion directly within Inspire Science. We think that that's a great way to take the work that we're doing, which is funded by federal funding for the most part, National Science Foundation funds and other things that your taxpayer monies and mine are moving toward, and leverage that for new understandings and for new areas to help many, many more students gain the reach that things like this curriculum can have in some of the marvelous ways that I think you'll see it happening. So we're very excited with this partnership to be bringing the research and these ideas to the work with McGraw-Hill and Inspire Science. So what's the stuff that we do? Well, I'm going to show a few examples of things that are interesting, cutting-edge examples. These aren't necessarily things that are in Inspire Science, but who knows? You know, with the way technologies is accelerating, 5 or 10 years from now, you may well see them in the classroom as well, and we think that they can be in the classroom sooner than that because we're doing pilots and research to show that it's possible. This is a thermal camera. It's an infrared camera that sees heat anywhere it is in its field of view. This is actually an older version of this. Now these things are much smaller. There's an attachment that works for your iPhone that will turn your iPhone into a camera like this. It's amazing actually how these have increased, by the way. These used to cost $10,000 not that long ago. This version you're looking at costs about $1,000. Now something the size of an iPhone that's a dedicated device is $200. So these are becoming much more accessible. And the reason that's important is because they can uncover phenomena that are all around us that we never would have known. I'm going to show you something. This is an infrared camera image of a cup of water. It's blue because the cup of water some of the water is evaporating, like happens for you when you step out of the pool. You feel a little bit cooler. So it is cooler than the air around it. But I'm going to hit play, and I'm going to show you what happens when we do something very simple. We're going to place a single piece of paper over half of this cup of water. And I want you to watch what happens as that piece of paper comes down. So if you're seeing this, you're noticing something very unusual, which is that the part of the paper that's over the water is red. That means that not only is it warmer than the water, the cool water that you're seeing in a glass, but it's warmer than the air around it. It's warmer than the environment around it. Energy is not supposed to work that way. Things aren't supposed to automatically get warmer. Everything's supposed to spread out and cool down. So what's going on here? This is something that mystified the people who, from our group, who worked with this. And I'm wondering if people have any ideas. So let's move to the chat. What do you observe? Why do you think this is happening? How can this happen? How can something get warmer? Energy can't be created. We know that, or we think we know that, right? Give us some time for people to mull that over and put some messages in the chat. I can guarantee you that this isn't magic. I can guarantee you it's not a perpetual motion machine or something like that. So I'll give it another minute here. I'm not seeing messages in the chat, but it may be that things aren't coming through, which is fine. Or it may be that you're all bashful out there. Maybe I should have had everyone introduce themselves. One of the things I want you to think about as you're thinking about this is thinking about evaporation and what that actually means. One thing that we know is that when something's evaporating, the liquid is disappearing. At least we don't see it anymore. But we know that it can't be just disappearing entirely. We know it's got to go somewhere. So the question is, where is that liquid going? That's directly tied to the question of what's happening in this glass of water. And I'm going to show you something that's an example that might help trigger some ideas in your head as you think about this. So let me show you a simple simulation, relatively simple, of something very similar to this cup of water. So these are all molecules. We could think of them as water molecules. And this is a cover that's been placed over them. I'm going to hit play on this simulation, and you'll see these bouncing around. Now, as I remove the cover, watch what happens and watch which molecules are the ones that something happens to. I can show the attractions between these two. So some of these are disappearing. They're disappearing because they're at the top. And notice that they're not all disappearing, so these aren't yet. But the ones that move fast enough and get nearest the top are the ones that leave the water. Now, if we remember what happens when things move fast, when we think about temperature, we can understand what's happening over here at the right, which is that when temperature rises, molecules move faster. So the ones that are moving the fastest are the ones that have the most thermal energy. Those are also the ones that leave. So as they're leaving, they're taking energy away from this. This is cooling down. But where does that energy go that they take with them is the real question. Well, if we think back to that cup of water, we realize that that piece of paper that was placed right over the top was capturing those molecules. The highest energy molecules, the ones that were leaving the water, were getting trapped on the paper. And they're carrying their energy with them. So we really are seeing evaporation, energy that's being carried with it, with our very eyes through that thermal camera. It's absolutely fascinating. It stumped us for a long time. But it turns out, when we actually thought about it, that there is a 10-molecule layer thick layer of water that's being deposited on that piece of paper, and you're seeing that with the camera. Truly, the invisible becomes visible and explorable when you have things like that technology. Here's another picture I just love to show because it tells you other invisible mysteries that are around there that we can sense with technology. This is a picture of a moth. The moth before, if I'd shown you this about 2 minutes earlier, would have barely been visible because it was the same temperature as all the surroundings. But it turns out that this moth actually wants to move. And in order to move, it needs to heat up. And what it does is use some of the energy it got from its food and heat itself up in order to move. So all the pictures before this had the moth facing a different way. This was the final picture of it heating itself up enough that it can move and then take off and fly. Interesting concepts, fascinating things you never knew were going on, and mysteries of the world around you that this kind of sensing technology can help us understand. So we've seen through all different kinds of research, people who study this, including us, that conceptual change, understanding about the world around us, can really be changed by technology. And in particular, I'll show you some examples of visualization, simulations, and other examples that show how technology can really help us understand differently. These kinds of technologies can help accelerate and promote students' knowledge about general content. They can support students' understanding about processes of science. They can support conceptual change, so understanding that moves from things that they thought were true about the world but really don't make sense when you think about it from a scientist's point of view, to understanding the world the way that we in scientists and experts understand it. And they can help students understand multiple levels that are involved in science concepts, so things that are very small, things that happen very slowly or quickly. We'll show some examples of how this can happen, but I just wanted to note that the research is really becoming clear that models and simulations can help students understand things more quickly and more effectively. Sometimes one thing I was looking at said 25 or more percent more learning, sort of better achievement can come from these kinds of simulations. Other things showing that students can do things faster using simulations than otherwise. Sometimes if students use simulations, there's research to show that they are more effective at doing things hands-on after they've used the simulations. So there's a lot of research that goes to show that conceptual change really is more powerful and accelerates when we use things like these simulations. So that's why we do what we do at the Concord Consortium. We like to take technology and use it to its fullest extent in what we call a deeply digital fashion. So this is not just using a PDF that you can highlight. This is really taking advantage of the full capability of technology to help students learn most effectively, because we want to do right by her. We know the technology can do a whole lot, and we know that if we design it well, if we look at the research on learning, that we can design things as effectively as possible and really help increase the potential that we have for her in the classroom. So let me move on to some examples. I'm going to show some examples that have to do with practices. You're probably familiar with the Next Generation Science Standards. These are great, and I'll say they're great for a few reasons. They're great because they give us a different view on learning that I'll talk about for a second, but also because they rest on research. This document, if you haven't seen it, you can get it online. It's available from the National Research Council for free, and it's the document that the NGSS were based upon. It's built on work from the last 20 years of research on learning, and it really laid out the framework for how we should understand what students should know and be able to do today. And it's on that all of the next generation science standards are based, and this structure as well. So this is the structure that the next generation science standards take. It's got 3 different dimensions to it. In the middle, you can see that there are these core content areas: life sciences, engineering, earth and space sciences. At the top, you can see what are called the practices of science and engineering, the things that students should be able to do. I'll talk more about those in a minute. And at the bottom, you can see these concepts that cut across all of science: scale, systems, energy, causation, patterns. When we think about learning in this framework, we're thinking about learning in a new way that really has these 3 dimensions together. So we just showed an example, for example, with the Moth, where we were seeing some idea from life sciences, but we were doing more than just learning facts about it. We were asking new questions about it, and we were thinking about concepts that are important across all of science: energy and change. Those kinds of combinations of taking practices and core ideas and cross-cutting concepts are at the heart of the kind of science that needs to happen throughout the next generation science standards. So we just talked about asking questions. Those are things that we think technology can really spur. We asked some questions about what went on in that cup of water. We asked questions about that moth. All kinds of things like that students should be able to do. They need to be able to have the habits of mind of asking questions and asking scientific, testable questions, and being able to distinguish questions that are scientific from questions that are non-scientific. Another thing students need to be able to do is to design solutions. When we think about engineering, we're talking about not doing investigations, but designing solutions. Technology is something that can help that in very interesting ways, and I wanted to spend just a minute showing an example of technology that we've developed to work with engineering ideas in all different ways. This is an example of a technology. This is a project funded by the National Science Foundation. This is called Energy 3D, and it's designed to help students think very easily and quickly about design of buildings and about the energy and science that goes into those. So as I'm talking here, I'm going to design a building myself, and I am making it very simple. But the concepts that go into it are relatively complex. If you've thought anything about buildings and their design, you know that energy is a key concept involved in that, and that energy from the world around us is the main thing that helps buildings interact with that world. So if I make a big picture window on this building, I need to think not just about my view, but I need to think about the fact that there is the sun around it. And that sun is moving all the time. And when that sun is up, then energy is coming down at that building, might be coming in through the window. In this case, I placed this house in a place where the energy is not coming in that window. That might be a good design, or it might be a bad design. We want students to be able to think about that. At the same time, we want them to think about all the different considerations that go into this, not just in the virtual world, but in the real world. So as we've designed this and designed curriculum around this and researched how this helps students learn about engineering, how it helps them think about the energy that's coming in different places, we can look at that in detail. We can see that there's a lot of energy coming in that side, not as much on the other side. We also want students to do this in the real world. So we even arranged this technology such that students can build these buildings themselves by printing them out and creating them in the real world. Then they can take probes and sensors and place those inside the buildings. They can use actual lights, and they can examine their design in the real world, and they can use the virtual world to design it. And we can accelerate students' understanding of how they think about the science and the engineering fitting together. At the same time, we're watching what they do behind the scenes, and we're developing new work on grants that help give them feedback as they go through that process, so we can understand that learning better. So that's an example of how we can help students understand how to design solutions, and we can accelerate their understanding of those ideas about engineering by using technology. Much more quick to approach a problem by being able to design it and redesign it 3 or 4 times in the computer than it would be to simply design that in the real world. Students would give up very quickly. Another thing that technology can leverage in really important ways is how to help students understand and develop models. What are models? Models are things that are simply representations of phenomena in the real world. Models can take a wide variety of forms. A drawing is a model of the world around us. A chemical equation or a mathematical equation is a model of the way the world works. Simple three-dimensional models of the body or of molecules are also models. But students also have models in their heads, models that represent the way they think about the world. And we want students to be able to develop those conceptual models in ways that match the real world and to build on their understanding as they go forward. We do that using a different kind of model, so models and simulations to help students understand these ideas. One of the examples of this is by helping students take actual models but leverage them in an interesting way to build their conceptual models. So I want to show you 3 different movies. And these are movies from a project that we have from the National Science Foundation called Sensing Science. This project is aimed at cutting-edge work, thinking about how we can use technology and our understanding about conceptual change to accelerate students' conceptual change in kindergarten about the matter that's around them and how heat and temperature affect that. So I'm going to show you 3 different movies and some examples of what we're doing to help students in kindergarten and younger primary grades think about heat and temperature and about what matter is made up of. This first one just shows some technology that we use with this. We call it the thermoscope that helps students explore different temperatures and think about activity in materials and how it's related to those. So I'm going to show it, and I hope that you can hear it. Sharon will come in if you can't hear the audio and let me know. And we'll look at this and I'll sort of show you how we've used this toward helping students' conceptual understanding in the next videos.
This is
don't worry,
water.
they don't spill the water, but they're as eager as every kindergartner you and I know.
Class.
It went right there.
Yeah, this.
Can I see how hot it is?
Yeah. Where's our tray? I guess I need.
I got cold.
Oops, you got it.
Cold water is cold.
Cold water's cold.
Cold or hot? Cold. See,
As they dip these probes in, you can see that the visualization is changing speeds.
Is that hot water?
This is hot water. So I'm going to put the same amount of hot water in here.
Now we're gonna. This is going to be sweet.
Is it going faster?
No, yeah, mine is going so
boy.
fast.
Okay.
And then colder. And mine are slowing down.
So already with that technology, you're seeing students think about temperature in simple everyday objects like water in ways that might be different than we expected before. So we're getting them to think about that in new ways. But to help them really build a model of what's going on, we've introduced some simple visualizations and a fun story to help students think about this. So we introduced what we call the land of bump. The land of bump has the red hots and the cool blues. And as students look through some scenarios with this, they start to see connections between what they did in the sensing technology you just saw there with things that play out in these scenarios. And they think about what that means for heat and temperature. And I want you to watch 2 of these short videos and think about what's going on with these students and realize that much of the research didn't think that at first that even young children could think abstractly. We now know that that's definitely not true. Babies can do algebra in their heads in interesting statistical ways, and young children are very capable of abstract thought. And now with this technology, we're starting to look at how we can unlock that and really get students thinking about things in a very sophisticated way. So here's an example of students playing with the land of bump and thinking about it.
It's time for the Red Hots to go on the dance floor and practice their routine. What do you think is happening?
I feel like they're bumping together. They're bumping together. What are we doing?
And what happens when they bump together?
They change colors. Oh, I get it. And every time one's gold meter.
Okay.
And they defense that when they move, they change the heat and the temperature.
So they've already started to make some very interesting connections about what's going on inside that representation. And now if we help them think just a little bit more, we help them connect that to the real world.
Do you remember what it looked like when we would put our probe in the hot water?
Yeah.
What happened? It was on the screen. We had two circles on the screen. And what was in those circles? Do you remember?
No.
Little dots that moved around.
Oh yeah.
And how do they move? Do you remember?
They move slowly and fast. And they're saying things on here. And diagonal and straight.
So slowly and fast. And which ones were fast and which ones were slow?
The blue ones were slow. And the red ones were fast. So they're saying things. Yeah, and every time they bump into each other, they lose on how hot they are because they slow down and get cooler.
I love that. So that's a student making a totally new connection that, trust me, I've tried to teach these kinds of concepts to middle and high schoolers that can be very complicated to understand the nuances of even at much higher grades. But by using technology, by making connections, we've accelerated that conceptual understanding, in some cases by years. Those are the kinds of things that are really powerful and fun as well to think about because they help us understand what we might not have yet even tapped into. So if we think about the ways that we did teach this at college and in high school in the past, it was very complicated. We used to use overhead projectors with ball bearings and shaker tables moving around. Now we can do this much more easily. At the Concord Consortium, we've been developing for over a decade something we call the Molecular Workbench, which is a molecular simulation engine that simulates essentially the whole molecular world. And it takes algorithms that research scientists use to simulate molecular motion, but it brings them to a level that's very accessible for students and teachers and puts a pedagogical layer on it that makes it both fun but also accurate at the same time. That's something that we've used in partnership with McGraw-Hill in Inspire Science to help students think about ideas such as phase change in ways that are accurate. So this that you saw was the Molecular Workbench. Here's an example of an interactive from Inspire Science where we help students think about temperature and particles. And in giving them some simple interactivity, we help them look at what happens when they change the temperature and get a very clear feel for the fact that solids and liquids are very different and that gases are different than liquids, but not entirely here. So as I let this go, we'll see it bubble, and we can see that these particles are moving much more quickly. Students can explore this, and they can explore this at will with a number of different substances. So that was ethanol, but if we change the substance, then these things are different. This is ethanol. If I look at that, I've got ethanol pretty cool here, and it already looks like it's almost a liquid, if not a gas. And I turn this up, and right away we can see that it becomes a gas much more quickly. So there are differences between different substances, but they all have similarities. They have similar properties, they have similar ways that they act. Students can explore that and see it very quickly and easily. And that allows them to build up that conceptual model much more quickly and easily than they could without exploring something like this. So I'm going to take a pause here and let anybody ask questions if they want. And I'll go on. I'm going to show some more examples of the work that we've been doing using our research findings and background in partnership with McGraw-Hill for Inspire Science. So if there are questions, I think we'll see them in the chat, although I haven't seen.
There are a few in the question box.
Okay.
Someone
Why
asked
don't you translate?
what grade level is this designed for?
Excellent. That's a great question. So as a research and development organization, we get grants that help us develop things across all sorts of grade levels. So many of the things that I've been showing have been designed for a variety of grade levels. So for example, the engineering work with the house is work that we've used in some upper elementary, but very much used in middle and high school. Some of the other work with molecules that's very sophisticated is used in high school or even college, but is very appropriate in the simple versions for elementary school. Obviously, the most recent thing I showed, we've developed in kindergarten and second grade. So as an organization, we develop things across the board, really exploring the possibilities of this technology. The Inspired Science curriculum is a K-5 curriculum, and we've developed examples specifically for different K-5 grade bands for use within Inspired Science.
So we have another one that says, what program was the last one called? So I don't know if that was your last simulation.
Right, so I showed a molecular simulation that's from what we call the molecular workbench, and that's something available on our website that I'll show more. The one before that with the kindergarten students was from a project called Sensing Science, also funded by the National Science Foundation. That's been exploring students' conceptions, young students' conceptions of heat and temperature, and how we can use technology to help explore that. There are a few others there as well. That all of them you can find on our website, which I'll show at the end.
Okay, a few more here. How closely aligned are your simulations to NGSS?
It's a great question. So we pay great care to aligning to the next generation science standards in most of the work that we do. The work is funded at different times, so there's some work that's been funded earlier before the next generation science standards. But with that said, even then, the content is still fairly closely aligned. And the best alignment, and I've been showing some examples of this, is also to how these kinds of technologies can bring out the practices of science and engineering. The things that we used to call inquiry all in one big lump, now we understand these as all of these different practices, and like asking questions or conducting investigations, and technology is ideally suited for pulling those things out together with the content areas. But the short answer is we pay close attention to the NGSS, and I'll show a link to some of our work at the Concord Consortium and how that's been connected to it. The short answer for Inspired Science, again, people from McGraw-Hill can say it better, but it's really as far as I understand it, one of the first, if not the first, I think, elementary science program targeting the NGSS. All of that work, all of the things in Inspired Science are directly designed for the NGSS.
Yes, Inspire Science is built for NGSS. And the last question before we continue, is it possible for a teacher to record a screen video capture of a simulation, adding a voiceover, and sharing this as a video on YouTube for a flipped classroom project?
So the short answer is yes, and it's a yes and or a yes but. So yes, it's certainly possible because all of the technology I'm showing is available on computers, either downloadable or in most cases available right in your web browser. And if you have any kind of screen capture technology, and there are some that are free for short videos as well, it makes it very simple to record a screen share of something and use some voiceover. The yes and or yes but piece is to say, if you are considering work that has a flipped classroom to it, I would also encourage you to think about the fact that you're making the assumption that those students already have some technology on the other end of things. And if they have the technology to hit play on a YouTube video, they also have the technology to hit go on a simulation and to use it themselves. So you might think about doing two things. You might think about recording a short intro and helping students frame a question. Maybe you're framing a driving question or a very simple idea that helps students think about things they might explore, and then include a link. And in a YouTube video, you can also include clickable links. Include a link directly to a model or simulation, like some of the ones that I'm showing. They run on an iPad, they run on a phone relatively well with modern phones too, and certainly run on computers. And have students explore that themselves, so that they're taking some of the time they might have spent watching somebody talk about a simulation, exploring the question themselves and coming with their own ideas to the classroom. I can't think of a better way to flip a classroom than to have students coming with their own hypotheses and ideas and ready to talk about them. Great,
Okay,
so I'm
that's
going to
all the
move on. There'll be a
questions. Yeah.
as well, so we'll be collecting those as we go on. Those are great questions, and I'm thrilled to hear them. So I wanted to talk about a few other practices, but in these cases I want to show examples of how we've been working with McGraw-Hill and Inspire Science to take the work that's come from our research work and apply that to things in the Inspire Science curriculum. The first example I'm going to show has to do with planning and carrying out investigations. This is something that's really critical for all of science. Students need to be able to know how to plan investigations and how to conduct them themselves. When we thought about this together with McGraw-Hill, we thought about this for a variety of examples. One that I can show here has to do with performance expectation in the NGSS about adaptation. Students need to understand that some organisms survive well, some survive less well, and some can't survive at all in a certain environment. And when we think about that, we can look at what simulations can do for students in that and give them some real capability to explore. So we want to give them some choice. Here I'll let this happen in the desert and hit play. And when this happens, let me reload this page. I think it may be that something's going on in this one. I don't know why that is happening. Let me try loading this up in another browser here. My web browser has been acting up recently, so if that's the case, then I'm going to move on if this doesn't work. But I'm going to try this in a different browser for a second. That's probably why. Okay, I'm going to switch back to this and see if some of these other ones work. Let me switch to this for a second because this is another example of the same idea of conducting investigations. If I play with this, this is a chance for students to examine things that are going on in a world around them and to conduct investigations at a very simple level. So I'm going to give you some context for this. And if we've got time, I'm going to flip back to that other one. This is a case where we're thinking about students in first grade and thinking about how they can look at information and information processing. Thinking about animals' body parts, how they capture certain information that they need for growth, and how they respond to those inputs. So if I move forward here and look at this, I've got some bugs and I've got some lights. And this is a very simple way to get first graders thinking about inputs for animals. And notice that some of them freeze in the light there. If I think about this and let this look at how many bugs are in this area, then I can make a graph of these bugs. But you know what? Same thing is happening here because I think I didn't load this again. So let me very quickly reload this. And my apologies here. Oops, I need to go back. That's not there. Let me see if this works for me or if I have to. There we go. That'll work. Okay. There. So if I wait for a little while, so we give students a chance to explore with this. And then once they've explored a little while, you see that we've moved past that exploration stage to making a graph. Now if I click on this make a graph, we'll see the first time here this leads students right through it. And it allows them to look at the results of their investigation and analyze these data directly. So we can see already that there are more bugs in the dark area than in the light area. Now, we've given students a chance to play with this at this little level, but now we're going to give them the chance to think about this more consciously. So do the same experiment. I'm turning on some lights. And as I do this, we look at what happens, and then I get to choose when I press the graph button. And when I do, now it's not going to make the graph for me, but it's going to help me look at how we form that graph and think about the results. So here's one. Is it in the light? Is it in the dark? Yep, there we go. Okay, that one looks like it was in the dark as well. So this time, All of these bugs were in the dark. One of the great things about models and simulations, I'm going to reset this and run it again, is that the path isn't predetermined. So that students have a chance not only to explore, but they have a chance to get different results. So we've just deliberately designed these for replayability so that students can go back multiple times and see what's happening. In this case, we got a couple of these that were in the dark, but many more that were in the light. So students can explore experiments just like they would in the real world, and they can find different results multiple times. And if students do this a few times in a row, they will start to see very quickly that more of the times than not, these bugs tend to move away from the light, but some of them tend to be in it. So this gives students a chance to explore ideas, conduct investigations, and come out with data that they can analyze in a way that's really rich and robust and let students have their own ideas, explore those ideas, and then talk about them together. That's what we've tried to do with all of the different examples within Inspire Science, is to give students the chance to investigate them in new ways and explore those ideas in a sophisticated fashion. We're running a little short on time because I want to leave some space for questions. So I'm going to skip forward to the last one of these, which embodies all of the pieces that I just described, but I want to highlight this question of argument and evidence. So when we talk about the practice of argumentation, we're not talking about having arguments and getting mad. We're talking about arguments the way scientists would. So scientific argumentation means having an idea, making a claim, and supporting that with some evidence that you find from the world around you and having some reasons for that. This is a very important thing for students to be able to do. It's what scientists do all the time. They do it in presentations and papers, and they do it in the hallways, saying, I think that this is happening. Other scientists say, well, I'm not really sure. It could be because of this. What's the evidence that points you to that? We want students to be able to do that all the time. And we've done that within the models and simulations that we thought about for Inspired Science. Here's an example from 5th grade. This is an example where we're having students think about the human impacts on different systems in the Earth, having them realize that human activities have major effects, and they have had them, on everything from land, vegetation to the ocean, but the fact that we can do things to help protect Earth's resources and environments. If I look at that, this is the situation that we have. We're giving students a chance to make some decisions and to send out boats and to do some fishing. So I'm going to send out the boats. I've chosen to send out 3 here. And in order to fish, I just click on the boats themselves. So I'm going to do a bunch of fishing here because I'm a little bit greedy. And as I go along and fish, we can see that over on the left, it's giving me a tally of the number of fish that are caught. And if we look in the middle, it's giving us a graph of the fish population in the lake. Now I'm making my own decisions of how often to fish. I made my decision of how many boats to send out to begin with as well. And I'm watching the data as I go. You can see that there are a couple different parts to this graph. You can see that the fishing season just ended, and now the boats have to go back to port. While that's happening, we can look at the stock of fish in the lake, and we can look at a graph of that, and we'll see the non-fishing season passing by here. And you can see the fish population recharging. I'm going to be greedy again and send out 3 boats and continue to fish the same way I was before. But I want to watch what happens as I do that, because when we think about human effects, we're thinking about not just effects at one given time, but we're thinking about the cumulative effects over time and the kinds of feedback loops that occur within that. Models and simulations are an excellent way to help students think about all of those feedback loops and about the kinds of things, for example, in human activities, that need to be imposed sometimes on the world in order to maintain a certain static nature of what you want. So if you want to have a certain number of fish available, for example, in this case, we need to think about the kinds of policies you might put in place. That's very hard to get across just by talking about it. But by looking at a model or a simulation, you can start to play out many different scenarios and start to explore things like what kinds of rules might you put in place, for example, for the frequency of how often you can fish, for the number of boats that we can allow, or it might be a number of fishing permits, etc. I think you can already see there's a pattern developing here, as I'm trying to maximize my abilities in that last round. I fished about as hard as I could before, but I only got 300 fish compared to 687 before. Now I'm fishing a bunch, and maybe I'm getting a few more, but I can guarantee you I'm not going to match what I got the first year. So if students play this across the course of a few years, they can quickly see that just trying to be greedy and take one strategy isn't going to satisfy the needs of everybody. It might satisfy environmentalists' needs if you think about different roles, but it's not going to satisfy the needs of of that over time if you limit the people, because limiting people is the simple rule. But if you're a fisherman, you certainly don't want to be limited. So this gives us the chance to explore very nuanced topics in ways that don't have a set pathway. So I'm doing this all with one strategy, but we could be doing this in a way that was an interactive classroom activity where students might decide certain rules and try them out. They might decide that certain groups are going to explore what happens if they only have 3 boats and fish continuously, or they decide that they can only fish once every 5 seconds. Really, when you start to use something like a model or simulation like this, the sky's the limit in terms of the kinds of explorations that you can do and the ways that students can start to understand this. And we think it's only through things like this that we can give students that deep conceptual understanding as quickly as we can. Otherwise, things don't hit home as easily. So I'm going to pause there and sort of show that as the last example of this kind of technology that we're working on with Inspire Science. The example that I wasn't able to show here because I hadn't loaded it in my browser properly was an example where we're using the same kinds of things with hawks and rabbits. Some of you have seen that simulation, looking at different colors of fur on different habitats. That's an example where in the 3rd grade we're getting students to think about these data. By the time they've gone through that example, they played at first with the different situations. Then they're allowed to choose an environment, to choose 3 or 4 different colors of coats on the rabbits, and to see what ends up in the population. They get a bar graph of different color coats for different situations. Same kinds of principles apply. They're able to investigate things widely. They're able to choose their own questions. They're able to to replay that multiple times and do their own investigations. So we think this is important because it allows you to explore ideas that you couldn't explore otherwise, things that happen too quickly or slowly, things that happen at different scales, things that are tiny, things that might be too dangerous to explore in the classroom. Those are the kinds of things we do all the time at the Concord Consortium. All of the work that you've seen is available on our website, concord.org, and you can sign up. You can sign up whole classes and use these materials at learn.concord.org to explore how these things work in our classroom. Our work is funded by mostly federal grants. We give that work away for free. It's open source and it's available for you or anybody to use. And as I said, you can sign up for it. We also have, somebody asked about NGSS alignment. We also have a pathfinder for our work at concord.org/NGSS, which lets you choose a practice and a cross-cutting concept and a core content area and see a whole list of resources that are available for free to use within those ideas. You can follow more about our work here on Facebook or on Twitter, and we're really focused on doing this. We'd love people to use our work or to tell more people about it because it's our mission as a nonprofit to get that out there in the world. But we're also very excited to partner with McGraw-Hill to be thinking about these kinds of things. And the examples that I showed you here today, there's a free opportunity for a demo account at inspire-science.com that you can use to get into the materials, look at how they're organized, look at the ways that we've used technology and how they've pulled together some other marvelous partners, including some people I've worked with in the past very closely to bring the best of research on learning to the science curriculum for elementary and really accelerate conceptual change through technology. So I'm going to leave it there. There are some people who created photos and things. Those are freely shared and available. I want to be thankful for them. But I'm going to turn it back to Sharon